Forgive me, I had to write geometric sequences in cursive because I like writing G's in cursive, and because my sister's name starts with a G. Anyway, so geometric sequences, they have common ratios. That's how you're going to get from term to term. So on this first one, I think you could probably just look at it and tell that 5 times 4 equals 20, but it would be a good idea for you to double check that it's times 4 each time. And yes, we have confirmed it is times 4. So that is the common ratio. If you want to write R equals, that's great. Here is where it's like, okay, I think I know what's what. If you can't figure it out right here, there's no shame in looking further up the sequence. For example, I know for sure to get from 36 to 18 that is multiplying by 1/2. And if you're like, oh, dude, I saw it as divide by 2. You know what? That's not wrong, but I'm going to encourage you to look for the multiplication. Or, you know what? Take that and then just make it a fraction, okay? Make it multiplication, which in that case would be a fraction, right? So, but there's one thing I'm missing, and it should be negative, right? Because we went from a positive 36 to a negative 18. So now backing up, is negative 72 times negative 1/2? You know what? Sure enough, that is 36. And is 144 times negative 1/2 negative 72? Yes. So our ratio is times negative 1/2. In fact, I'm going to get rid of the x on here. I'm just going to say R equals negative 1/2. I like that better. Number 3. Okay, well, now I'm looking at this going, I don't know how to get from here to here to here to here. There's no facts that just jump out at me. So here's how you find any common ratio is you're going to say, okay, take a term. So a term, and you're going to multiply it by x. And that's going to equal the next term. So 24x equals 84. And then solve for x. So I'm going to divide by 24. And doing this without a calculator, I'm looking at this and I see that I can divide them both by 4. So I would get 21 over 6. And I can actually divide that by 3 and by 3. So I get 7 halves. So my common ratio is 7 over 2, at least from here to here. Now, it wouldn't be a bad idea for you to go ahead and try multiplying 84 by 7 over 2 to see if you get 294. It turns out you do, by the way. It's a good idea for you to check them all, because as I gave an example in class that I was like this, I was like, hey, listen, what if it was 5, 10, 20, 40, and then I wrote 60. So this is times 2, that's times 2, that's times 2. That is plus 20 because it's not times 2. Well, so then this would not be a geometric sequence. And if you're asking, well, what is it? It's just some numbers. Doesn't have to be anything, right? Number 4, determine whether the sequence is arithmetic, geometric, or neither. This is a good example of neither right here. It's neither. Because the other option was, well, this was plus 5, plus 10, plus 20, plus 20. It's not linear, because linear would just be a constant rate of change, meaning it would be like plus 5, plus 5, plus 5, plus 5. And so that didn't have that, so it was neither. Number 4, how they got from this term to this term looks like they just moved the decimal one place, right? It was here, now it's here. And then again, to get from the second term to the third term, looks like they just moved the decimal one place from here to here. So what is that? That's times 10. So is it geometric? Is it arithmetic? Is it neither? It's geometric, and it's because our common ratio is 10. So if you're like, well, what's a good way to explain something? The second you say it's a common ratio, it's geometric, okay? Now, if I said common difference, that would be arithmetic, right? All right, let's jump to number 5. Let's see, 86. I'm feeling like this one might be arithmetic. Let's check. If I subtract 15, okay, so this one is arithmetic, and it's because my common difference is minus 15. Now notice over here, it was R equals 10 because that was a common ratio. And notice right here, it's D equals negative 15 because that's a common difference. Do you see the difference? Sorry, I didn't mean to, no puns there intended. Okay, this one has me feeling like it's going to be geometric because we do not see it go from positive to negative and it be arithmetic. So, well, okay. I don't know off the top of my head 4 times what is going to give me 10. So what I'm going to do is 4x equals negative 10. Divide by 4, and I get x equals negative 5 over 2. So let's see, is negative 10 times negative 5 over 2? What is that? Well, let's see. I get negative 50 over 2, well, positive 50 over 2. That's 25. So this is neither. And it's because there's no common ratio. And it's definitely not a common difference because, like we said, it bounced from positive to negative. And if you're like, I don't get it, why would that, how do we automatically know it wouldn't be linear if it went positive, negative? Because think about it. If we were at positive 4, then negative 10, and then positive 16, and then negative 28, how are these 4 dots linear, right? You could also ask, how are they geometric? That's a different scenario because in theory, they are doing this, okay? And in theory, those are geometric, but exponential. So anyway, so back to this, it was neither. Next, well here, I automatically see that this is times negative 1/4, right? Because 7 times what number is going to equal negative 7 over 4? Well, if you were to divide that by 7, negative 7 over 4 divided by 7 is negative 7 over 4 times 1/7, which would be negative 1/4. Why did I do all this? Just to kind of show you, prove to you that 1, you could do it without a calculator, and 2, that's how. So let's see. It's 28 times negative 1/4. Is that 7? Yes. But you know what? I don't know about 1/12. If I were to multiply that by 1/4, also known as just divide it by 4. So 1/12 divided by 4, that's 2, we get 8, that's 3/28. Is that right? Oh, and then, yes, so that's right. Okay, because we would get 28 if we multiplied 1/12 by 4. So yes, this is good. The common ratio is negative 1/4. That means it is geometric. Right, the next 3 terms of the geometric sequence then graph the sequence. So we're pretty sure, or I'm pretty sure that's times 6 times 6 times 6. In fact, I know that is. So and then just graph the sequence. Okay, I can do that. Here's the sequence. The first term is, oh, hold up. I'm going to need that to be flipped around like this. The first term is negative 2. I'm just going to write negative 2 like that. The second term is negative 12, so I'm going to call that negative 12. The third term is negative 72. I'm going to call that negative 72. I'm kind of just estimating here. I'm not really going for super accuracy. And then negative 243, I mean, dude, that's down quite a ways, right? So here's what this looks like. If you're a little nervous on what it's supposed to look like, it's supposed to look like that. Kind of like that. Okay? It would be technically a growth equation because it would look like this. Right? It's growth. Our b is 6. It's just flipped upside down. So here, this feels funky, right? But I'm going to focus here, And I'm going to do this. 6x equals 10. Divide by 6, and I get that x equals 5/3. So let's verify that we are multiplying by 5/3. What's 54/25 times 5/3? Well, that can do that. 3 can go into 54, let's see, 18 times? Yeah, 30 plus 24, okay. So we would get 18/5, and yeah, we did. Okay, so I'm pretty sure our common ratio is times 5/3. And if you're like, that seems really gross, I get it. It does seem kind of gross. 54/25, by the way, I'm not going to come up with an exact number. I'm really going to think of it like 50/25, which would be 2. Okay, so what that means is the first term is roughly 2. Oops, I shouldn't put that there, right? The first term, let me close that off, is like 2-ish. And then same thing with 18/5. 18/5, that's like 15/5, which is about 3. Second term, about 3, just a little bit higher. Third term, 6. So maybe about right there. Fourth term, 10. So maybe about like that. So it looks like this. There are our graphs. All right, we got our equation up here for geometric sequences. Remember, n equals the term number, and r equals the common ratio, and that's about it, really. Oh, and I guess a is our first term, sort of, right? Because there is an a right here, so it just, maybe we'll just say it deals with the term, okay? Now, let's zoom in here. Write an equation for the nth term. Then find A6, okay? So first thing I want to find our common ratio. Yeah, I'm pretty sure it is just times 5. That feels funky to say, right? But think about it. Times 5 times 5. If you were to multiply 3/5 times 5, well, the 5s would cancel, giving you 3. So, as you saw in class, you might not want to do all of the math to truly find the whatever term. Like we did a 10th term, and the answer was 20-something million. I don't want to do that. So we could do it here, though, because this is 1, 2, 3, 4. The 5th term is 15, right? And the 6th term was that 75. So, I mean, there's the 6th term. Not that bad, right? But that's not the point. Okay, so let's write the equation. We have a sub n equals our first term. How do I know that? A sub 1, right there. And we're following this formula. So here, let me erase all that around it just to kind of clear the air so we can focus on it. That's our first term. First guaranteed term right there. Now, that is times what? It's times the common ratio. The common ratio was 5. And then we're going to raise that to the n minus 1 power. So we're done. Believe it or not, that is one part, that is the other. If we had plugged in 6, we would plug it in right here, and we would get it, okay? And in fact, but how would I get that? Well, 5 to the 5th power, I mean, then you're going to multiply it by 3 over 125, right? Next, let's see, to go from here to here, that's times 8. And then let me just verify that 1.6 times 8, that's 48. Yeah, and then this is 80, so it's 128. Yeah, we're good. Oh, and yeah, decimal once, 128. Okay, I'm going to get rid of that. So we're verified that our common ratio is 8. So here we go. A sub n equals 0.2, because that is our first term. times 8 to the n minus 1 power. There's the first part of the answer. And so since I didn't do it on the other one, I'll do it on this one. A sub 6, because we want the sixth term. How do I know that? They said find A sub 6. So that's the sixth term. 0.2 times 8 to the 6 minus 1 power. A sub 6 equals 0.2 times 8 to the 5th power. And I have no idea what that is, but I just looked it up on Desmos, and it's A to the 6 equals 0.2 times, you ready for this? This is 8 to the 5th power. Only 32,768, right? And then multiply that by 0.2 times that, and you get 6,000. So A sub 6 is 6,553.6. That is the sixth term. And in fact, I wasn't expecting a decimal. I sure was, right? We had a decimal right there. Is it possible that there was no decimal? Yeah, I guess possible, but it didn't happen. Number 12. Oh no, they've given us a table. It's the same thing. First term, second term, third term, fourth term. That's what this is. First term, second term, third term, fourth term. They just have communicated a little bit differently. So, looks like we're multiplying by negative 1/10. How do I know that? Because the decimal was here, and it looks like it moved back 1. It was here, and it looks like it moved back 1. It was here, it looks like it moved back 1. That's times 1/10 if I've ever seen it. And then also it goes from positive to negative, back to positive, back to negative. The only way you're going to get that is with a negative right there. So here's our formula. 2,436 times negative 1/10, because that's our common ratio, to the n minus 1 power. Putting that in a box. And then I'm just going to go on Desmos and type all this in with a 6 right there. It probably will not surprise you that A sub 6 equals negative 0.02436. Wait, that has a 2436. Yeah, you're right. Because if we move it 6 times that way, notice how it moves once, twice, 3 times. So if we were here, right there, then this is the 5th time, and now the 6th time. So there is our answer here. All right, I'm not looking here because I can look right there and I see that this is times 1/9. Now, if I were to multiply 18 times 9, would I get 162? 9 times 8 is 72 plus 90. Yep, 162. So bye-bye. We are confirmed that it is the common ratio is 1/9. So A sub n equals negative 1,458 times 1/9 to the n minus 1 power. There's our first answer, and our second answer is A sub 6, where I'm just going to hop on Desmos and plug a 6 in right there. In fact, here, I'm going to show you exactly what I type in on Desmos. You know what? I'll do a screenshot. There it is. I do not have to type 6 minus 1 like that. I could definitely put a 5 there. But I do that in case maybe I want to graph it next and I want to change that to an X. And then I have to think for one little split second less. Okay, now you might be a little freaked out. We never did a word problem, but you can do this. So here, let's read it. An archery competition begins with 256 competitors. Well, that's the first term, 256. After the first round, which that's our first round, right? After the first round, 1/4 of the competing group remains. So it would seem like we are going to multiply by 1/4. That would be our common ratio. Okay? And then, let's see. Hang on. So let me do some highlighting. 1/4 after the first round. And then after the second round, 1/4 of the now smaller competing group remains. And then the last round is where there are fewer than 5 members in the group. So, which round is the last round? Well, here's what we're going to do. We want to know when it is 5 people remaining or less, right? So that would be like 5 is greater than or equal to, and this part's not that super important, right? But we're going to go with it anyway. 256 times 1/4 to the n minus 1 power. Okay, so if you're like, oh, how am I going to do this? Well, you could technically write out what's happening. 256, what's a fourth of that? Let's see, 64, and a fourth of that is 16, and a fourth of that is 4. So it didn't take us that long. First group, second group, third group, fourth group. And this number is less than 5, right? Less than or equal to. So which round is the last round? The 4th. And if you're like, but wait, how would I have known to do that? Okay, the other option that I could have said is, well, what if we went back to like the lesson that we did before this? This is 6-6. What if we went back to 5-6 and we said, listen, let's graph this and this in Desmos. We could have done that. We could technically do a little bit of solving. We could have divided by 256. We could have done that, and we'd have gotten 1/4 to the n minus 1. Now, I don't truly think you would have done this, but again, this is 1/4 to the n over 1/4, so you could multiply it by 4. No, you couldn't have. You could have multiplied. Hang on. Let me get my thoughts straight. So we got that, and this could technically flip up. How does it flip up? Because when you divide by 1/4, that's the same as multiplying by 4. So we would have 5 over 256 greater than or equal to 4 times 1/4 to the n power. And then we could have divided by 4, which would look like this: 5 over 256 times 4. Anyway, I'm just saying we could have even graphed these two separately. These two separately. And at any rate, maybe, I'll pause and do that. So here's the Desmos representation of this. And if you're like, what? There's a big purple part? So this was the less than or equal to 5 part. So at the 3.83th round, well, we can't have 3.83 rounds. So it would have to, sometime between the 3rd and 4th round, we get down below 5. So that's why it's the 4th round. So if that's a little bit too crazy, sorry. I guess I shouldn't say sorry, but I'm just saying this is how you could have approached it, okay? So how many players are in the last round? Coincidentally, it was 4, right? What is the 10th term? Oh, we're done with that one. What is the 10th term of the geometric sequence with this? Ooh, interesting. So a sub n equals a sub 1, right? A sub n equals a sub 1 times r to the n minus 1. Well, okay, hang on. If we said a sub 3, then we could have a sub 1 times 2/3, and then this would be 3 because of this 3, and then minus 1. So let's see. Oh, you know what? We actually know a sub 3, so we could erase that. And a sub 3 is actually 8 over 3, right? There's a sub 3. So if you're like, I'm lost on what's happening, what we're going to do is we knew this, we knew this, and we knew this, so we can solve for that. And if you're like, no, I can't, yes, you can. 8/3 equals a sub 1 times 2/3 squared. So from there, 8/3 equals a sub 1 times 4/9. And you could divide by 4/9, or you could multiply by 9/4. And here's what would happen. The 9s cancel, the 4s cancel. That's a sub 1, duh. 3 goes into 9 3 times. 4 goes into 8 2 times. You get a sub 1 is 6. So then you could just say, all right, well, listen, a sub n is 6 times, what was it, 2/3 to the n minus 1 power. That's your formula to where you would plug in 10 and 10, right? But let's say you didn't think to do it this way. How could you have possibly done it? Well, we had the third term. 8/3, and we know that the common ratio is 2/3. So when we go this direction and we're told it's a ratio, you are multiplying. So if you were to go this direction, you'd be dividing. So we could actually back this thing up. 8/3 divided by 2/3. Well, that's 8/3 times 3/2. The 3's cancel. Here, I'm going to change colors to do that. 3's cancel. 2 goes into 8 4 times. So the second term is 4, right? It's not writing. Zoom in. 4 right there. And then here, we could keep going. 4 divided by 2/3, which is really 4 times 3/2. That's 2 goes into 4 twice. 2 times 3 is 6. So check it out. We could have found the first term, I don't want to say the hard way, because who knows, that might have felt like the hard way to you. But you can find it with a formula. You can find it by just, I'll call this like just figuring it out. And then you go grab a calculator, because I don't think any one of us wants to do 2/3 to the 9th power times 6. So I'm going to pause and go do that. All right, there we got it. 6 times 2/3 to the 10 minus 1 power is 0.156. And again, remember, we were getting larger numbers going backwards, but if we were to continue going and we were to go 7 more steps into the future, 0.15, I mean, yeah, it's getting, each number is getting cut it by 2/3, right? So smaller and smaller, we're going to get smaller and smaller. Last one, find the sum of the terms of the geometric sequence. Explain your reasoning. So before you get all googly on me, what if we were just trying to add this up? So first of all, obviously 1, he's going to be out front. 1/3 plus 1/9. Okay, well that would look like this. This would be 3/9 plus 1/9. Okay, that's 4/9. And then plus that plus a 27th. Okay, well, so that would mean that this is 12/27 plus 1/27. So that's 13/27. And I mean, even the next term, let's see, what's 27? The next term would be 1/81. So again, this would become 39/81 plus 1/81. That is 40/81. So let's see. This was 1/3. And then when we added a 9th, we got to 4/9. We got closer to half. And then this, if we'd had, let's see, like 18.5, that would have been half. And then dang, 40/81, that's pretty close to half. And then I don't want to keep going, but what if we said it was 1.5? Like, what if that was your answer and then your reasoning was, hey, listen, I added up the first 5 terms and that's what I got. Cool. I'll be accepting of that because you're going to have to Google this one. Like otherwise, because there is an actual formula, not one that I'm going to ask you to have or use, but this was just the challenge of it, right? Just the what would that be like? So here's what it would be like. If we have infinite terms like we do here, then here's the formula. The sum equals the first term over 1 minus the common ratio. How would you have known that? I don't know. So here's the sum. The first term was 1, and then 1 minus, and we said the common ratio was 1/3. So let's see, that's 1 over 2/3. And then if you were to do 1 divided by 2/3, and you were to do this, let's see, that's 1 times 3 over 2. The sum is 3 over 2, which is, guess what? 1.5. Isn't that crazy? That I kind of was like, hey, what if we just kind of guessed this thing? Because here's the deal. We started at 1/3, and then, like I said, we got a little bit bigger. And then that made us get a little bit bigger, and that made us get a little bit bigger. And this number is super close to 1/2. In fact, if it had been 40.5 over 81, it would be exactly 1/2. I wrote 1/5. Be exactly 1/2. So let's just, again, for like, to be crazy, 81 times 9, 81 times 9, 729. So listen, if we would take 40 over 81 plus 1 over 729, how tiny is that number, by the way? So we would, do you think that if we were to add this, we would reach 40.5 over 81? No, we will not, but we would get, let's see, hold up, I did 81 times 9, should have been 81 times 3. Okay, hold up, let's back up. Like this, and this would be 1 over 243, but the concept is the same. How tiny is this number? If we were to add this in, would we get to 40.5 over 81? No, but we would get to 120 243rds plus 1 over 243, and that would equal 121 over 243. Well, again, if we had 121.5, that would be exactly 1/2. So here's just the crazy thing is, if infinitely we are adding teeny tiny pieces, because the next one would be that 729, like I was saying, then eventually it would add up to be about 1/2, okay? And there was 1.5. So hopefully you might have found that like slightly interesting to think about. And that is our assignment for geometric sequences. See ya.